So I'll be using both whiteboard as well as the PPT. Okay, direct drive. So you know, the main characteristic of the direct drive friction welding is that the moving part, which is to be joined, is connected to the some work holding device. Workpiece holding device. Okay, and this is again connected to some kind of the spindle, which is driven by some electric motor. Okay, but between the spindle and electric motor we have the brake and the clutch arrangement. So the brake and clutch arrangement both are here, so that once the desired friction time has been achieved, desired temperature has been achieved, so that the brake can be applied after disengaging. So this is the kind of arrangement. So you have first electric motor, then you see here electric motor, and then in between you have the arrangement for brake and clutch. Okay, and then you have the spindle, which will be connected to the work holding device, and then workpiece. So the workpiece is here, work holding device, then and the spindle and the brake and clutch and the electric motor here. This is the kind of setup. On the other hand, again we have workpiece and then work holding device, and then a fixed kind of arrangement, where from like we can apply using some hydraulic arrangement, the force can be applied. Okay, so here we need some kind of the like say axial pressure application arrangement, which is mostly so that you can apply the controlled magnitude of the axial pressure, say 5 kilonewton, 10 kilonewton, as per your requirement. Okay, and another thing that we need here is the some kind of controller which can allow the different stages for friction welding, like how long there will be a workpiece will be rotated to develop the frictional heat. Thereafter it will be disengaged, and then the forging pressure will be applied. So there will be need of the controllers for controlling the different aspects of the weld cycle time. Okay, and then we need the displacement controllers for controlling the displacement, so that the predetermined amount of the upsetting is realized. Displacement controllers in order to achieve the desired upsetting. Okay, so so that you can develop the desired quality weld joint. So this is one aspect, and if you want to see this, so this is like the electric motor, then the brake and clutch arrangement, and the spindle, work holding device, and the workpiece, both the ends. Okay, again the work holding device this side, and the arrangement for applying the desired pressure. Okay, so here what we do initially, if you would have seen, the workpiece is rotated and then speed is kept constant. So in case of the direct drive arrangement, the friction speed remains constant. this is one important aspect. And once we achieve the desired temperature, the forging stage comes in. Okay, so that's what you will see in these diagrams. See, initially there is a gradual rise in temperature, and then that remains constant. Temperature also remains constant, speed remains constant, and then you see once at the end of this stage we apply the things are disengaged, the forging pressure is applied, so that the significant upsetting can take place. So in the second stage, upsetting is there but not much. The major forging action takes place in the third stage only. Another thing you will see, when the two metals come in contact and the enough heat is generated, so initially the torque needed for rotation, that will be fluctuating in a particular manner, then it becomes constant. In the later stage also it increases, and then it starts decreasing. So the upsetting and the temperature, these are the two things are primarily shown. My idea is to show this temperature and the burn off related thing, like what are the different stages as far as the heat generation and the upsetting is concerned. So that's what you can see here. Initially there is a little heat generation where rise in temperature takes place. This is the second stage, and third stage major upsetting takes place during the joining. If you see the direct friction welding, in case of the direct friction welding, you can have you see, this is the case where the one workpiece is fixed and another is rotated, so you have rotary friction. And in case of the linear friction, there is a reciprocating movement with a very small magnitude but under high pressure. So the linear friction, there is a just like in ultrasonic welding with the small magnitude, but at lower frequency this is done. So at the interface, frictional heat is generated to develop the joint. And in orbital welding, if you will see again there is a rotational movement that is used for non-circular section. Okay, so now if you see again the things related with the direct friction welding with regard to the rotational speed remains constant in direct friction during the frictional heating. Once the desired temperature is achieved, we apply the force. So the friction pressure remains constant, and on application or on realizing the desired temperature, the friction the forging pressure is applied. So if you see, it always takes some time to come to the standstill. And so if you see here, the time versus the rotational speed is concerned, during this braking time period, the speed is coming down. Okay, speed is coming down. Certainly it will not become a standstill. So somewhere in between the start of the braking and end of the braking, where the RPM is reduced to 0, somewhere in between the upsetting pressure or forging pressure is applied. So first friction pressure and then upsetting pressure. So this is not immediately after the application of the brakes to stop, but somewhere in between the dead zero and the beginning of the commencement of the braking. So the time between this time when we are having the start of the braking and when the forging pressure is applied, this is being defined as a waiting time. We have to wait for a while so that the speed is somewhat reduced, then the forging pressure is applied, and during this one only the major upsetting will be happening. So the upsetting, if you see where the upsetting is, the duration in which the upsetting is taking place is this one, and the magnitude of the upsetting that is being realized you have seen with the greater clarity in the previous one, but here this is what the upsetting will be taking place, the significant upsetting will be taking place. Okay, and likewise these are the two initial stage of, initially there is a little increase in the torque required for continuous rotation due to the softening and more firm metallic contact with each other, and similarly at the end when the forging pressure is applied. So these are the different components which are showing the different stages. Let me log out this. How much time it takes to stop, affects the weld quality. Let's say you apply the brake here at this stage. Okay, so speed will is getting reduced from say a given RPM to the nil RPM, or it takes time this much to reach this stage of the complete stop. So when the braking is applied, you see when the brake is applied, it takes some time to come down, and thereafter you expect that the forging pressure will be applied here or will be applied here. So if the forging pressure is being applied after a long delay, because you have longer waiting time when the braking time is more, this will be reducing the temperature at the interface. So the long braking time are not actually good, because these will be reducing the time, reducing the temperature at the interface when the forging pressure will be applied. So basically what we'll say that the weld temperature and forging time both are badly compromised in case when the delay, the time required to stop is significantly more. We always expect that this is done as quickly as possible so that the forging can be realized when the temperature is high enough and as quickly as possible. Okay, and that is why what we say that the forging phase starts somewhere in between the application of the brake and the complete stopping phase. Another important thing related with the friction welding or direct friction welding is like how the RPM of the moving workpiece is going to affect the things. So you know, you don't apply the forging conditions or forging, you don't achieve the forging stage until you have the desired temperature at the interface, and the desired temperature at the interface is function of what? The frictional heating, and the frictional heating means where from it is coming. There are three variables that will be affecting the rise in temperature at the interface, and these are like say the rotational speed. Okay, this is one, and then the pressure which is being applied, like say the friction pressure which is being applied, and the time for which this heating is being done. So through the control of all these parameters, see all these parameters are interdependent. Lower the RPM, you need higher pressure and longer time. Likewise, higher the RPM, you need maybe lesser pressure and the lesser time. So a combination of all these three is achieved in such a way that the desired temperature is achieved as fast as possible, because we don't want to have very long the frictional heating time. Why? Because let's say you need a temperature of 800 degrees centigrade at the interface. So frictional heat, maybe you can generate 2 kilojoule per second, 2 kilojoule at the rate of 2 kilojoule, or 0.5 kilojoule. So depends like what you can generate, at what rate you can generate, and that will be the function of the rotational speed, friction pressure, and the time. So at what rate you are generating. If you are generating at lower rate, you need longer time. So let me show you another plot. If you are generating higher, if you are generating the heat at a higher rate, you need the shorter time. Like say the heat generation rate. If you are generating at a higher rate, then you need the lesser time. If you are generating the heat at lower rate, then you need longer time. Okay, for generating the same amount of heat, the desired amount of heat, so that the predetermined the forging temperature can be realized. So there are issues related with the long time and short time. The short time is beneficial because you are achieving the desired temperature at the interface in a very short time. So heat dissipation to the underlying base metal is very limited, and therefore you get the narrow heat affected zone. On the other hand, when you are working with the low heat generation rate, then you take longer time to achieve the desired temperature, and in meantime lot of heat will be dissipated to the underlying base metal, and that will be leading to the wider HHL. Okay, so it is important that at what rate you generate the heat, and that significantly determines on these two things only, because time is another kind of factor, because we are talking about the rate of heat generation. So the RPM, rotational speed, and the like say the pressure, the friction pressure that is being applied. These two will be determining the rate at which heat will be generated. So we, considering the system capability, considering the forging pressure that you have to apply, say there is a limit on the friction pressure that we normally apply. So what is the independent parameter left in? You can rotate the sample at say 500 or 1500 or 4000 RPM. That will be changing the rate of heat generation significantly. So what we do basically, like say for steel welding, you may need, okay, let us apply the particular kind of the for a given size of the job. Okay, say for a given size of the job, peripheral speed that is normally applied for the speed is for the steel welding, the typical surface speed which is needed ranges from the 75 to 205 meter per minute. Okay, so that is what you can realize depending upon the kind of RPM being used and the diameter of the job. From pi dn you will get the surface speed of the sample during the welding, and the kind of force. So from this you can determine the rotational speed. Okay, and the forging pressure that is applied, like say the typical friction pressure is of 75 MPa, and forging pressure which is applied is of 140 MPa. So these are the kind of typical parameters for the steel welding. So if you see, if your the job size is small, so what should be the RPM that you need as compared to the job when it is of the large size? So here is one more logic behind this use of high RPM. Use of the high RPM of the moving component results in the low heat input friction welding, which in turn lowers the heat affected zone. Okay, and this is primarily used for welding or joining of the hardenable metals. So we prefer the high RPM for a given job size in order to realize the low H-net and reduce the heat affected zone. Now, can you tell or anybody tell how the RPM is going to reduce, high RPM is going to reduce the net heat being supplied during the friction welding? Anybody can comment? High RPM is going to help in achieving the desired friction weld using the low heat. How can, yeah, oh good, that's right. So that is why initially it looks a little odd and different, like high RPM we are seeing lower speed, but we are reaching the desired temperature quite early, and that is helping us in achieving the desired welding temperature easily in lesser time. That in turn will be reducing the heat dissipation or heat requirements in total for developing the joint. So it's good, means the people are attentive, that's good. So next is our now let me see if anything else process, that is the inertia drive. Inertia drive friction welding. So you know, so as I said, there is a very large size the flywheel, okay, which is again powered by electric motor, okay, and then there is again brake and clutch arrangement, and this will be connected to the flywheel. Okay, further to the flywheel there will be like a spindle, and a spindle will be connected, work holding device, and work holding device to the workpiece. So workpiece, then workpiece holder, and then spindle, and then flywheel, okay, and then there is a brake and clutch assembly and electric motor. So this is the kind of general arrangement you have. So what we do in this process, using the electric motor, you connect the flywheel through this clutch, okay. So clutch will be helping to connect the electric motor with the flywheel, and so the flywheel is powered. So when you are giving the power, flywheel will be rotated, and you wait until the desired RPM is achieved. So flywheel means it's a heavy mass, okay. So the mass of the flywheel you can adjust as per need. Say typical electric motor, say, will be rotating at 3000 RPM, just for an example I am giving. and you have say 50 kg. You can adjust it to the 60 or you can adjust it to the 40. So how it is done? You keep on adding the wheel weights. Weight, say you have one wheel, then another wheel, or a smaller wheel, larger wheel. These you can keep on adjusting the wheel weights. So basically wheel weights are adjusted in order to adjust the inertia of the wheel. Okay, so what we do, the wheel RPM is increased initially. You see, let's see, wheel RPM is initially, say it will be starting from 0 and then it will be a maximum RPM that is to be realized of the flywheel that will be achieved first. Once you achieve this RPM, rotational speed of the flywheel, you disengage the flywheel from the electric motor. So now you have given enough mechanical energy or enough energy to the wheel. This energy is identified. Basically you try to identify the energy required, energy to be imparted to the wheel. Once if you have identified energy to be imparted to the wheel in form of, like say, the RPM achieved and the mass of wheel, these are the two important variables. And once it is achieved, then you disengage, okay, and then apply the friction pressure. So when the friction pressure is applied, it will start, speed will start decreasing, right, like this. Okay, and somewhere in between, when you find that your temperature has see, up to this temperature is fine, there is no rise, but the temperature has been achieved, desired temperature has been achieved, you apply the forging pressure. So I'll explain these things using the simple diagram. Okay, here using the PPT for better clarity. You see this, there is a large wheel, there is a large wheel like this, which is imparted the desired RPM with the help of electric motor, and at other end you have the moving part, and then a stationary part is pressed against this moving part. Okay, so initially you give the desired RPM to the wheel, or so to the rotating to the wheel which is coupled with the workpiece. Okay, and once the desired RPM has been achieved, you apply the friction. You see, this is the stage. When you achieve then you apply the friction force. So during the friction force, certainly the frictional heat will be generated, there will be rise in temperature, but due to the frictional effect, the RPM of the workpiece or the wheel will keep on reducing gradually. Okay, when you find that the sufficient heat has been generated, rise in temperature has achieved, you apply the forging force like this. So there are two variants. In one variant, we don't apply the additional forging force, but whatever is the friction welding force has been applied, it is kept same until the end, but you keep on applying, or you apply the forging force at a particular stage. Or alternatively, this is another option where you apply on achieving the desired temperature, forging force is increased so that upsetting can take place. So initially upsetting is very limited, but the moment when you apply the forging force, significant upsetting takes place like this. So this is the upsetting kind of thing. And this is your the inertia friction welding, and if you see the cycles are completely different in this. This is the direct drive, here also it was, this is the direct drive, this is also the direct drive, and if you see the rotational speed and the application of the frictional force, these are a little different from So if we have to talk about the differences or comparative study of the direct drive and the friction welding, okay. So here what are the things that we have, like direct versus inertia. So in case of the direct, what you have basically, your the rotational speed is constant, okay. On the other hand, during the friction stage, your rotational speed, basically this is the friction stage, rotational speed is constant. But here in case of the inertia, it is reducing or decelerating, reducing speed in the friction stage. This is one important difference as far as the inertia and the direct friction welding is concerned. And what you need more here is to uh, you have to have a good control over the energy being imparted, to the flywheel, to control the good quality of the weld. But in case of the direct welding, you can continue to do the frictional heating as per your need, although all those parameters are well identified and optimized so that the process can be automated. Okay, another important thing, so the variables here in the inertia welding are like, say, the wheel size, or you can say its mass that is being applied, the speed that you are going to realize, rotational speed, and the axial force that you are going to apply. There is another important aspect about this friction welding. Like what you have seen, there are stages like the frictional heating, okay. Once the desired temperature has been achieved at the interface, during the frictional heating, okay, you start applying the forging force and pressure, so the upsetting can be realized. So certainly at the end of the frictional heating, when you apply, the temperature should start coming down. See, this is the frictional heating stage. Once the frictional heating has been stopped, forging is taking place, temperature should come down. Obviously it will be coming down gradually in the braking phase in the direct drive. But in case of there is no braking phase as such in case of the inertia drive. The speed of the moving workpiece will be reducing on its own during the friction stage as well as the forging stage. Okay, so here, but instead of the temperature coming down so easily, it holds up actually in the forging stage. So it doesn't come out, it doesn't drop rapidly. Any reason for this? Can anybody comment on this? You see, frictional heating has been stopped. Temperature should come down rapidly depending upon the cooling rates being imposed during the upsetting stage. But the temperature doesn't drop. Temperature doesn't drop that rapidly, but temperature holds for a while, or it reduces gradually, not rapidly, in the upsetting stage. Anybody can comment on this situation? Though I think it can be said in more simple and straightforward way. Like although the heat comes from the two sources in the friction welding. One is your frictional heat, and the second is the deformational heat. In the initial stages, frictional heat dominates. Okay, in the second stage, in the forging stage, it is the deformational heat which dominates. Okay, but even this holding is also not very good enough to avoid the undesirable metallurgical changes. Okay, so this holding of the temperature is basically attributed to the deformational heat which is being generated. Okay, this is the simple point, that is what I wanted to make here. Now coming to the different aspects related with the friction welding, you can say the metallurgical aspects of the friction welding. So there are the friction welding is can be used actually for both similar metal joining and the dissimilar metal joining. So initially we'll talk about the similar metal joining. Similar metal joining. Okay, so what do we need as far as the metallurgical characteristics or the metal properties are concerned? What properties are of the great importance for facilitating the friction welding? So you can say simple properties needed for friction welding. So there are basically two properties about which I will say the similar metal joining. The two properties are crucial. One is like the forgeability. All of you know, everybody will agree about this. We have talked. There should be some percentage of the elongation or ductility. At the same time, moderate, if not very low, moderate yield strength. If it is low, it is good. So the yield strength and this one is good. But what about those which don't have these kind of characteristics, like ceramic to ceramic, or cast iron to cast iron, or cemented carbide? These kind of the metals, you see, you cannot do the friction welding for the similar metals. Certainly, if you have a softer metal, then these materials can be joined with the soft metals. So you need another soft metal for joining, like say ceramic to the soft metal. It's fine, or cast iron or cemented carbide with the softer metal, it is fine. Probably you can do, at least there is one which can participate in the joining process. This is one. And second, all metals do not contribute effectively in friction welding. Why? Because what is the most prerequisite thing in friction welding, apart from, like say, the ductility and the forgeability? And now this is important thing. I want your inputs or your thought process. Like the most important thing, what is after the forgeability of a metal, what is the next important thing to develop a friction weld? Okay, heat generation is important. So how the metals affect the heat generation? So because that will form the basis for like which kind of metal can be done, which kind of metal cannot be done. Certainly forgeability, you see, heat helps in forgeability. Even if the metal is not having much of the forgeability, certainly it can be improved with the heat generation. But what is that property that is influencing the heat generation? So certainly it is the heat generation that is metal's ability to generate the heat. There are multiple metals which come with the solid lubricants. And if the metals are having the solid lubricants, then certainly they cannot contribute much in case of the friction welding. For example, there is free machining steel, which are intentionally added with a high percentage like 3%, 5%, 2% of the sulfur and lead. So addition of these elements help in breaking the chips. Okay. Likewise, if the metal is having high percentage of the graphite also acts as a solid lubricant. So if the metals having the solid lubricants, then how can they generate the frictional heat? Okay, so that is why the metals should have the ability to generate the frictional heat, and those which cannot do this thing, at least they cannot be friction welded. And so the common metals, there is a huge family of the metals which can be welded like copper, copper alloys, iron, especially the steels, stainless steel, nickel, titanium, all these can be friction welded easily. Coming to the another important thing is related with the similar metal joining, which goes in favor of the friction welding only. That is about the similar metal joining using the friction welding is workable. Why? Because if you are having, let's say, these are the components of the similar metal joining using the friction welding, and here you have got the friction weld. Whatever your one side is affected, and in the similar way the another side is also affected. So at least you are getting either hardening or softening, the same is for both the sides. So this is good. Similarly, whatever is the kind of the heat dissipation one side, because of the equal K, you are having the equal heat affected zone both the sides. Same HZ, same hardening and softening. Okay. And the another important thing, since both metals are same, so their yield strength or a drop in yield strength due to the rise in temperature, it is same both the sides. So if the thermal softening is equal both the sides, so you can expect that upsetting will also be same both the sides. You see, both sides will be getting upset by the same amount of the magnitude, right? Like this. So if the upsetting is equal both the sides, so there is at least a symmetry in development of the weld. All these issues will be missed. All these good features will be missed in dissimilar metal joining. Similarly, here you have whatever is the expansion is taking place one side, and same is the extension or expansion is taking place other side. So there is no differential expansion and contraction. So you see, the expansion and contraction are not a problem in case of the similar metal, not a major problem in case of the similar metal joining. Similarly, the HZ is equal, hardening, softening is same, weld is symmetrical, upsetting is symmetrical. But in the similar metal joining, all things are different. You know, alpha is different, K is different, yield strength is different, thermal softening is different, and that is why you are finding varying HZ, somewhere softening and somewhere hardening is taking place, right? And somewhere more upsetting, other side less upsetting. So you are having a symmetrical weld. So all those are the issues in case of the, even in case of the friction welding, you come across all these problems apart from the metallurgical issues. at the interface. Okay, so on the dissimilar part I will talk little later. So these are the good things. Whatever the changes are taking place in similar metal joining, it is same. Hardening, softening, or HZ or offsetting, all are same or equal both the sides. But still, you have a large mass of the metal uh, behind the interface, which interface is being heated, say temperature of 700 or 800 degrees centigrade, and below that you have a temperature of base metal temperature 25 or 30 degrees centigrade. So this will be extracting or sucking the heat very rapidly, transferring the heat from the interface very rapidly, and that is why the kind of the cooling rates experienced are more than, in general they are usually greater than a critical cooling rate, especially for hardenable steels. So hardenable steels experiencing the critical cooling rate greater than the cooling rate, experiencing the cooling rate greater than the critical cooling rate in the vicinity of the weld interface or joint interface, then certainly you can expect the hardening of the HZ. So hardening and the embrittlement or loss of toughness, all these can be the issues in case of the friction welding of the hardenable steel, and therefore any steel, you see, any steel having the carbon equivalent greater than 0.3 or 0.35, you can say, they will need some kind of the precaution to restore the properties, because this will be leading to the embrittlement and all those hardening of the heat affected zone. There is no fusion zone, so certainly the heat affected zone, including the interface, that needs to be corrected or rectified for more favorable properties, and that is why the hardenable steel friction welds needs to be given post weld heat treatment, so that you can restore the elongation or the ductility, you can reduce the residual stresses, so you can say the stress relieving, and you can improve the toughness through the tempering. Okay, so improving the toughness, these are the different heat treatments only. So you can say the stress relieving or
does inertia welding work? Basically, by forcing together pieces to be joined in such a way that rotary motion and pressure are converted into heat, which literally bonds the pieces into one part. Two pieces to be joined are aligned in an inertia welding machine. One piece is held stationary, the other is rotated rapidly on a spindle chuck attached to a flywheel. When the flywheel reaches a predetermined speed, it is disengaged and the freewheeling piece is forced against the stationary piece. Friction between the parts heats the budding surfaces to forging temperature. Just before rotation ceases, the two pieces bond automatically. When the flywheel stops, the weld is complete.
for some time under the LINFRIC project. Low-cost linear friction welding is an area TWI has been interested in for some time under the LINFRIC project.